these limits. Along that axis, it's got to have a particular behavior. Oh, it turns out that I jumped the gun over here. All right. The 0th term may be one that's required. That's what stalled me a few minutes ago when I wrote this down and then I was looking over there to make sure that the potential goes to 0 at infinity. I realized that I was going to have a problem. So I unerased this. All of the L equal 1 and higher terms are 0. A sub L is 0. But the A sub 0 term could be there. So what I'm going to do is write that. Okay. Constant plus that. So the general solution would look like that. Okay? And the safest thing to do when you're solving a problem like this is leave it in until you get to the point where you're looking at what the rest of the boundary conditions have to look like. Right? All right. So yeah. So I have this. So let's figure out what terms I have to have in that expansion in order to get this along the axis. Yes?
But if the potential has to drop to 0 at infinity and A sub 0 is a constant, isn't the only way that that could drop to 0 is if A sub 0 itself is 0?
That's what I was thinking about here. This doesn't go to 0. At infinity. Yeah.
That doesn't really have to go to 0 because that's just an arbitrary statement that it's 0.
Yeah, because the field, the magnetic field is the gradient, and the physical quantity is the magnetic field, and the potential is just a construct, right? But I'm going to leave it in there anyway. And then, yeah, when we find the magnetic field, that constant drops out. I don't have to worry about it. Okay? But I left it in there because I told you we want to obey this, and we want that. All right? What?
I'm just trying to figure out how that doesn't go to 0 as you get rid of it.
This goes to z over z.
Oh,
It becomes 2 pi I over c.
I didn't see that as Z.
That's a z squared and a z.
Oh, okay.
All right. So I do need a constant there if I want the potential to go to 0 at infinity. But as Jake said, it doesn't have to go to 0 at infinity. It's just that I specified that I wanted it to go to 0 at infinity. All right. But as I said, I've got this is how I want to express it. And this is what I've got right now along the axis. So that's going to be for theta equals 0, cos theta equals 1 along that axis. All right. So what I want to do is somehow express this in terms of powers of distance, r here. Now along the axis, r is z. So I can start with this and expand it. Right? It's 2 pi I over c times, I've taken care of all the constants, 1 minus. Now, I'll assume that z is much bigger than r, just so that I can write an expansion. So I'll rewrite this as z is bigger than r, so I want that to be small. Z squared, that goes away. 1, this quantity is small quantity, right? The radius of the ring is small. If I want to make an expansion, all right? So now that I've done that, I can write that as 1 minus 1/2 r squared over z squared. That's first order term. Plus 3 z to the 4, 5/16 R6 over Z6. More terms. And along the axis, R is equal to Z. So now we can take a look at the Legendre expansion there and see which one of these terms would correspond. Right? So we find out that A0 must be minus 2 pi I over C. Right? If I want potential to go to 0 and infinity. Looking over here, I come to the conclusion that all even L's are going to go to 0 because I don't have any odd L's, odd powers over here. All right? So all the p sub L's for even L are going to go to 0. Right? And then I can look to see, okay, which ones actually end up corresponding here. I have B1 is 2 pi I over C times capital R squared over 2. B3 is 2 pi I over C 3 R to the 4th over 8. B5, I can find out what B5 is, right? So I actually have now, I can go term by term and figure out what the coefficients on each of the terms have got to be, right? And so I have now succeeded in expressing this scalar potential in terms of a whole sum in Legendre polynomials, right? In R, even though what I did was I figured out what it has to look like along the z-axis for theta equals 0, but the coefficients have to be the same along that axis as they have to be everywhere else, right? So this was an unusual way of finding the boundary condition. That's why I chose this particular case. In other cases, the boundary conditions are going to be more straightforward. Although I guess I have to say this. That is that in electric field problems, it turns out that the potential is a very useful quantity to have. For one thing, potential in itself, electric potential, has a real meaning. It's related to the electric potential energy. It's related to the energy to move a particle from here to there, right? The magnetic potential, this scalar potential here, doesn't have that kind of physical meaning. So we don't go seeking the potential just for the sake of finding the potential. We seek the potential in order to take its gradient and find the magnetic field, right? And therefore we don't actually solve potential problems in magnetics as frequently as we would in electric fields. Okay, so I've got this ring of wire over here, and I've now figured out what all the coefficients have to look like there. And I'll keep this here for the moment and erase everything else. You just say the problem is solved. But one of the strengths of this approach is that it allows us to see fairly easily what the lowest order term that contributes to the field that we're going to calculate is. Right? It allows us to simplify the problem for ourselves. For example, if I've got a really weird current distribution over here, right? So I've got now not a ring of wire, but a passel of wire, which is more typical of what you find in the box. When you go to the box, you find actually something more like that, all right? And somehow it got closed at both ends, and somehow you run current through it. but it's finite. And so what we can do, just like the electrostatics problem, right, is we're off at some distance and we view this and we ask, what does the magnetic field of that distribution look like? And this approach, which you've already learned, which you've already had some practice with, allows us to get a good handle on what the properties of that current distribution are. And again, this is something that comes in when, for example, we want to figure out what the magnetic moment, or rather, what this, the angular momentum or the spin of a quantum state is. What we do is we go out far away, we measure the properties of the field far away from that quantum state, and we find out what the lowest order terms are, and we say, ooh, it's got a magnetic moment. Or, ooh, it's got a magnetic dipole moment. Or, ooh, it's got a magnetic quadrupole moment. Scatter something off it and look for the interactions, right? So if we get sufficiently far away, so that definitely the distance away is much, much greater than the size of the current distribution, right? Then we can express that, the magnetic field, as being the field due to a whole series of potential poles, right? I'm going to actually exclude the possibility of a monopole at this point, but the arithmetic doesn't say anything about excluding monopoles. They could be there. But the lowest order physical quantity that we know of right now would be the dipole. And if I get sufficiently far away from that distribution right there, so for that special one, let me erase this. And I've got this at distance, I won't need this. I've done the matching and I have found the coefficients, right? Then I find that the magnetic field that points out in the radial direction is 2 pi I over c r squared cos theta over little r squared. And the magnetic field that points in the angular direction is pi I over c r squared sine theta. Oops, I screwed up here. Cubed. R cubed. The potential goes as 1 over r squared. The field goes like that, right? And so this is only true. This is for the ring far away, right? I still have all those terms there, but what I've done is to say when I get out to large enough r, the only term that's going to survive is when I take the gradient of that potential. When I get far enough away, the lowest order term is going to be this one, and the other ones are all going to go faster by 1 over r squared, or even faster than that. They're going to drop off. So this is going to be the dominant term far away. Right? If I shrink the ring to 0, it would be the same effect. So what I'm going to do is I'm going to define a quantity that I'll call m, which is I over c pi r squared. Current, whoops, capital R squared. That's the area of the loop of the ring, correct? Times the current, basically. Actually, I just write it as I area over C. And we're going to call that the magnetic moment. And then this becomes 2m cos theta over r cubed and m sine theta over r And that is the field due to a magnetic dipole. Okay? There are other terms for the ring, but you get far enough away or you make the ring small enough, and these are the terms that are going to dominate the magnetic dipole. All right. But we see here that there are other terms, and I just want to identify the other terms. When we worked with electric potential, we used a trick. Probably the word trick's not the appropriate word. I'll call it that. And that was that 1 over r minus r prime, absolute value. We're going to use the law of cosines for that. And then we can expand. And so this looks like 1 over r plus r dot r prime. R prime is where the current is. R is where you're measuring. R cubed. This is the distance from that point. Okay? And the reason that I can do that is that I'm going to start thinking about this as a little tangle of wire and current, like so, and the observer far away. So that distance to the center of the distribution is r. Okay? Plus other terms. I can expand this. So again, I'll just say we use law of cosines, and we expand in r prime over r, because r prime is very small. The distribution where the current is near the center of this system that we've chosen, and the point that we measure is far away. Okay? So I'm expanding in r prime over r. And then if I take that and I cube it, because I'm going to need that cube, then I just look for what the highest order terms, lowest order terms are. I should write this like that. That's 1 over r cubed plus other terms. Now we look back over there, we say, oh, that's the integral that we've got to do in order to find the magnetic field, or in order to find the vector potential. Take your choice, but I'm going to have to do an integral in that. Right? So in these integrals, I can now insert 1 over r and 1 over r cubed in the expanded form. And if I get far enough away, then only the lowest order terms are going to survive. Yes?
How is that 3 r dot r prime over r to the 5th?
Yes.
Is that just supposed?
Let me think about.
Yeah, that's correct.
It's correct.
Good.
Because they cube it, if you have that term 3
Yeah,
times.
cube it.
Then why isn't it just that cubed?
You've got all the cross terms.
Okay.
So we're looking at this times this.
Oh, okay.
I'll leave it as an exercise to the student to write out the first 5 terms here and then cube it. I'll leave it as an exercise to Eli. That's why I didn't write them out.
Okay. I'll bite.
Okay. Okay, so now back to this. We've got the dot products. The dot products are going to have cosines in them. So guess what? That looks like spherical harmonics. I can express that sum in terms of spherical harmonics. In fact, I can. So yeah, it actually looks like this. Legendre polynomials. Actually, I cheated here and I wrote it out in Legendre polynomials rather than spherical harmonics. Yep, okay. So now I've got that, so then the vector potential can be written out. And the vector potential looks like, and the magnetic field can be written out using that, but so the vector potential looks like that.
Is that sum of negative r prime over r to the end, or is that just a smudge?
That's a smudge. And this should be L. Thank you for asking.
Yep.
All right. That should definitely, yes, that's good. There's my L plus 1. Ended up over there. Okay. Over the wire. And I want to distinguish between, you know, we actually have a bunch of wire here. And so I have current running through the wire, and I'm going to say that everywhere inside the wire I've got the same current running. So this is a tangle of wire. And so I have current in the wire, and I'll put my current there. That is the definition, right, from over here. That's my current density, all right? But now I'm just integrating over the wire, the path of the wire, because I've done the rest of the integrals. Right? And current and DL are remaining. Okay, which now I can re-express that. R prime, no, don't need the vector.
Is that I over C or 1 over C?
This is I. Thank you. This is prime. P sub n cosine theta prime. L prime. So we're just integrating over the length of the wire. Correct. Yeah.
Does the loop have to be closed?
Yes, because the current has to be contained.
Okay, so we're just saying that there's no physical situation where you could have
Yeah.
a wire that
like
isn't
how we're integrating.
closed
Yeah,
and still
I
has
can
to
put the
be-
battery in there if you like, and that'll close. Correct.
Okay, so there's just like some because physics that happens.
Yeah,
Okay.
because physics.
Because physics, enough
Mathematics
said.
wouldn't have to have that.
Okay.
But we ain't
So, N?
Speak for yourself.
H9. Okay, so now back to here. So this looks like I over C. Let me write out a couple of terms.
It's kind of funny. I
One
think we're
over
going to lose like
R.
the last 2 minutes of class.
Oh, sorry. Oops, I got the I.
It would take longer to switch it.
I over C, right, times 1 over R, integral over the path. That's the first term in the sum here, right? That's the magnetic monopole term. So it's in there. But the integral over a closed path of a vector is 0. Comes back upon itself. So that term's going to be 0. But I'll leave it in there mathematically. 1 over r squared, integral over the closed path of, r prime cos theta prime dl prime plus, and other terms, okay? So that would be my first order term, monopole. Next